Alright, so in this video we go over section 8.4, Lagrange multipliers to optimize functions with constraints. Okay, so what's different between this section and the previous section? Because in a way we are going to do the same thing, which is find maximums and minimums of functions of two or more variables. But in this case, we are going to have a constraint. For example, in the previous section, we used the d-test to classify points as max, mins, or saddle point. That was called the d-test. So in this case, we are going to have a situation in which that is going to be more applied, if you will. For example, a company that wants to maximize profits and being constrained to certain budget, or some soft drink manufacturing wants to design a can for sodas that is the least expensive, but it can hold a constrained amount of 12 ounces of soda, right? So in this case, we are going to have this as our constraint, and then staying within a budget. Okay, so those are constraints. I mean, you can think of this like when you do in real life. You want to go shopping, you want to buy the most or the best, but you want to spend the least amount of money possible, or you are subject to certain budget. Okay, constraints. So constraints are going to be written in terms of equations, not in terms of functions. Okay, so every time we're given constraints, we need to write them with all terms on the left hand side and the right hand side to be a zero, because that's going to be our part of the constraint for a new function that we are going to construct to get maximums and minimums for, well, to optimize this function depending on the situation. Okay, so in a more general way, whatever we get on the left hand side, that's going to be our g of x, y, which is constrained. Okay, so given the following equation as an example, we have the equation 2y cubed equals 3x minus 1. They're asking us to write this constraint in the form described above. So all we do is move this 3x to the other side with the opposite sign, and this negative 1 with the opposite sign, which is 1, set it equal to 0. And this is going to be our g of x, y. Okay, so the next page is in which we describe the method of Lagrange multipliers. Okay, so we're gonna start with some function f of x, y, which is the one that we want to optimize, or that is maximize or minimize. So we're gonna call this the objective function. For example, if you want to maximize the area of some rectangular enclosed area, well, that's because that's our objective, to maximize the area, or to minimize the surface area in a different situation. And then g of x, y will be called a constraint, which is what we just defined in the previous page. So we're going to construct a new function called the Lagrangian function, in which we're going to have this fancy looking curly L of x, y, lambda. We introduce this new variable called lambda, which is the Lagrange multiplier. Ultimately, we are not going to look at this value, at least not within the scope of this course, but if you want to read about it, you can read it in the textbook. Okay, so we are going to construct this Lagrangian function by starting with writing the function we want to optimize, which is f of x, y, and plus lambda times the constraint function, which is the g of xy, which is why we sent all the terms to the left-hand side of the equation that defines the constraint. And then we are going to solve the following system of equations, which involves finding three partial derivatives. So to this Lagrangian function, we're going to take the partial derivative of L with respect x, partial derivative of L with respect y, and the partial derivative of L with respect lambda. Notice I'm giving you both notations, the Jacobian notation and the subscript notation, so you can see both of them. And I'm going to call these equations 1, 2, and 3. Okay? So, essential steps to follow when solving these equations. Well, we combine, once we get these partial derivatives and we create a system of equations, the first thing we do is to combine the first two equations to eliminate lambda. And then we are going to obtain a fourth equation. And then we are going to combine that fourth equation with the third equation from the given system, from the system that we set in the previous step. And we're going to do that to find the critical points. So in this case, to find the maximum and the minimum, we're going to plug in those critical points that we obtained in the original function. Notice in this case, let me give you a few useful facts about the process that we follow here, and some, if you will, some freebies here. So, something you will notice is that every time you find the Lagrangian with respect lambda, this is always equal to the constraint. Okay, so, and the advantage of this is that in this case we are not going to use second derivative test, which is what we call the d-test. Remember that tedious process? Well, in some cases it was tedious to find second derivatives. Remember that example, f of xy equals e to the x squared minus y squared? Remember we had to go through a couple of product rules with partial derivatives. We wrote a lot. We wrote quite a bit to go over a problem like that. So it gets a little bit more complicated. So in this case, we're not going to perform any test to determine whether it's max or a min. In fact, we will be told whether it's gonna be a max or a min. So as you can see in the first example that we are going to do. So in this case, if you look at example 1, use Lagrange multipliers to minimize the function. So in this case there, it is given, okay, it's given that we are going to have a minimum. Whatever we get, it's going to be a minimum, no need to test. Okay, and so we have the function f of x equals x squared plus y squared, subject to the constraint x plus 2y equals 30. So the first thing we do is to write this. Remember what we did with the equations? So x plus 2y minus 30 equals to 0, where this whole quantity right here is the quantity g of x, y, which is the constraint in that form. Now we are going to set the Lagrangian, fancy L of x comma y comma lambda equals to f of x y plus lambda times g of x y. Okay, so from here we're going to have x squared plus y squared, which is our f of x squared. Okay, so this guy is that guy, we replace with it, and we are going to replace this guy over here. So let's form that Lagrangian. So x squared, well, let me actually write it over here, L of x y lambda equals x squared plus y squared plus lambda x plus 2y minus 30. So I'm going to start from here taking the three partial derivatives. So I'm going to write these partial derivatives right here, right next to right next to the work I have. So partial derivative of L with respect x. So the derivative of x squared is, of x squared is 2x. This is going to be 0, and then inside of the parentheses, the derivative of x is the invisible one that we can see here. But this is 1 times lambda, which is lambda. The partial derivative of L with respect to y, it's going to be, well, it's going to be 0 over here because it's x squared, and then 2y plus the derivative of 2y, which is 2 times lambda. And then the partial derivative of L with respect to lambda. These two terms go to 0. What's the derivative of lambda? The coefficient is 1. Well, the derivative of lambda is, well, actually all this here, which is the constraint. X plus 2y minus 30. So now I'm going to form a system of equations. 2x plus lambda, set it equal to 0. 2y plus 2 lambda, set it equal to 0, and x plus 2y minus 30 equals to 0. So that's the system that we create and solve. So, and also let's label the equations 1, 2, and 3. So we set those three equations, and we are going to combine one and 2 to eliminate lambda. Okay, so I'm going to form a system of equations with the first two. So 2x plus lambda equals to 0, and 2y plus 2 lambda equals to 0. So when I form this system of equations, in order to get rid of lambda, so I'm going to multiply both sides of the first equation by -2. That's going to turn my system into the following one. It's going to turn it into -4x minus 2 lambda equals 0. The second equation remains the same. 2y plus 2 lambda equals 0. So when we add these two equations, we are going to get the following. We get these lambdas eliminated. We get to eliminate the lambdas, and we get -4x plus 2y equals 0. And then in this case, I'm going to solve for y. I think it's easier to solve for y than solving for x, because if I solve for x, I'm going to deal with a lot of negative signs, and also my x in terms of y is going to have fractions. So I'm going to solve for y to y equals 4x, and then divide both sides by 2. That's going to give us y equals 2x. So in this case, I'm going to call this equation 4. That's our fourth equation that we talked about in the description of the method in the previous page. So that's, if you will, the next step. Combine three and 4 to find the critical point. Okay, so I'm going to form a new system with the third equation, x plus 2y minus 30 equals to 0 and y equals to 2x. Okay, so in this case, I don't want to move this 2x to the other side to later use elimination the same way I did it here. Of course, if you prefer to do that, again, it doesn't matter how you solve a system of equations. You could use, again, elimination, substitution, reduce row operations with matrices, determinants, and I think I'm missing one. Graphing, I think it's another. So no need to use more complicated methods. So in this case, notice y is already by itself. So what I can do is plug the y over here, and that's going to give me x plus 2 times y, which is the 2x here, minus 30 equals to 0. So this is going to be 2 times 2x, which is 4x plus another x. That's going to give me 5x minus 30 equals to 0. 5x equals 30 and x equals to 6. So that's the x value of the critical point. Now we need to find the y value of the critical point using this equation. Y equals to 2 times x, which is 6. So 2 times 6 equals to 12. So our critical point, notice in this case we don't look at critical values. Critical values, we got them for functions of single variable, one variable. In this case we're talking about functions of multiple variables, so critical point. And it's already given that this critical point is a minimum because we were asked to minimize. So all we do is plug in f at the original function. So 6 wherever it corresponds, wherever you see the letter x, and 12 wherever you see the letter y. So 6 squared equals 36 plus 144, and if we combine these two quantities together, so that's 144 plus 36, we get 180. So that's the minimum value. Alright, so let's look at another example here. So the next example here, they're asking us to maximize the function. So it's going to be very similar. I mean, we're going to repeat the process essentially. But in this case, we are going to find the maximum. So, first of all, I'm going to write this in terms of a constraint for which the quantity here is g of x, y. Okay, so I'm going to form the Lagrangian function. So L of x, y lambda equals f of x, y plus lambda g of x, y. Okay, so that's what we're going to do here. So in this case, let me write this down. Lambda equals x, y, L of x, y lambda equals, so in this case, 12x, y minus 3y squared minus x squared plus lambda times this quantity x plus y minus 16. Okay, so what are we going to have here? So I'm going to take the first partial derivatives, but in this case I'm not going to list them. I'm going to take the partial derivative with respect x, and then I'm going to directly set it equal to 0. So Lx is 12xy. So the derivative with respect to x is going to be 12y, 0, and minus 2x. And then the derivative of x is 1 times lambda is lambda. And set it equal to 0. Lambda y equals, the derivative of L with respect to y, not lambda. This is L, not lambda. So the derivative of this with respect to y, we get 12x, and then minus 6y, and then the derivative of y is 1 times lambda. This is plus lambda equals the 0. The third derivative of the Lagrange function with respect to lambda this time, it's going to be no other than the constraint. And set it equal to 0. Actually, I don't need those parentheses. Let me get rid of them. I don't know why I wrote them. Okay. And that is our system. And again, let's label them. 1, 2, 3. So what are we going to do again? I'm going to combine 1 and 2 to eliminate lambda. So let's write the equations 12. Okay, notice in this case, I'm going to write this in alphabetic order instead. So negative 2x plus 12y plus lambda equals to 0. The second equation, it's already in alphabetic order, 12x. And so 12x, where is it? 12x minus 6y plus lambda equals the 0. So in this case, our goal is to get rid of the lambdas, and we can do that by multiplying any of the equations by -1. I don't know, I'm gonna do the second one. Why not? I'm gonna do the second one by -1. Multiply the second one by -1, both sides. Okay, both sides, and then, well, this is going to turn the system into, okay, the first equation remained the same. And the second equation becomes negative 12x plus 6y and minus lambda equals to 0. When we combine the equations together, the lambdas go away. And now we add up the x's to negative 14x and plus 18y equals to 0. Let's call this the equation 4. So now the next step is to combine 3 with 4. To find critical points. To find the critical points. So x plus y minus 16 equals to 0, and negative 14x plus 18y, and then that equals the 0. Okay, so I'm going to use here I'm going to use, maybe I could have simplified this equation. So in this case, what I did here is Well, we could do, because the numbers are kind of big. The numbers are kind of big, and I don't want to multiply for the top equation by positive 14, because this is going to give me a really big number. So I'm going to use substitution in this case. I'm going to solve for y or I'm going to solve for, yes, I'm going to solve for y. And so this is going to be 18 y equals 14x. And then I'm going to divide both sides by 18. That's going to be 14x over 18, which reduces to 7/9 of x. And this quantity right here, I'm going to substitute it over there on equation 3 precisely. So I'm going to obtain x plus y, plus rather y, I'm going to open parentheses, minus 16 equals to 0. So I'm going to write 7/9 of x. So I'm going to move this negative 16 to the other side with positive exponent. And you might want to find a common denominator here, 9/9, to have 9 plus 7. That's going to give us 16 over 9 x. Okay, so what's the next move? The next move is I'm going to multiply by 1 over 16 to eliminate this 16 with that 16 and this 16 with that 16, which will give us 1/9 of x equals 1. And then I'm going to multiply both sides by 9. And that's going to give us x equals 9. Now let's find the y for the critical point using this baby equation that we have here. So y equals 7 over 9 times x, which is 9. Divide this out, and this is y equals to 7. So our critical point only one critical point, by the way, is going to be the point 9,7. Okay, so now we need to find the maximum of the given function, and we do that by going back to the original problem, to the objective function f of x, y. Now that's what we wanted to maximize. 12xy minus 3y squared minus x squared, and plug in the values of the critical point. So in this case, f of, that's going to be 12 quantity minus 3 times quantity squared minus quantity squared. So x equals 9 and y equals the 7. Okay, so simplifying this, we are going to get the following. I get 12 times 63 minus 3 times 49 minus 81, and using a calculator we get 528, which is final answer. Okay, is it always only one critical point for this type of problems? Not always. And the next example will illustrate that. So for the next example, which I think is going to take a good minute to solve, because that's going to deal to a very interesting system of equations, that it's not going to be a linear system of equations the way we did for examples 1 and 2. So in this case, use Lagrange multipliers to maximize and minimize. Oh, this sounds like we are going to have more than one critical point. and we are going to find all of them. Okay, so for the function f of xy equals 2xy, which is the objective function subject to the constraint x squared plus y squared equals 18. Okay, so let's see what's going to happen here. Let's see. So I'm going to write this in terms of a constraint x squared plus y squared minus 18 equals the 0 in which this is going to be our g of x, y. And then I'm going to form the Lagrangian function x, y, lambda, which is going to be the objective function f of x to x, y, plus lambda times g of x, which is x squared plus y squared minus 18. Now, let's set up the system of equations. So L, the partial of L with respect x. Oops, I don't need the xy lambda anymore. I'm just going to write the answer here. I don't know what I was thinking. So this is equal to the derivative of this term with respect x is going to be 2y plus lambda times 2, so 2 lambda x, if you will, or 2x lambda, either way. And you might want to set it equal to 0 at once. The derivative of the Lagrangian with respect y, that's going to be 2x. In this case, the derivative of this term with respect y is 2x plus lambda times, so 2 lambda y. And the derivative of the Lagrangian function with respect lambda is the constraint. So, and set that equal to 0. And put the curly braces to denote that this is the actual system of equations. So, now how are we going to solve this system of equations? This one is going to be a very interesting one to solve. So, number one, before we move on, label the equations as 1, 2, and 3 for our reference when we combine this to number 1 to get rid of lambda, and number 2 to find the critical point. Okay, so what we do next is I'm going to combine uh, 1 and 2 to eliminate lambda. Okay, so now what's next? So let me write down 2y plus 2 lambda x equals the 0, and 2x plus 2 lambda y equals the 0. And this is a very interesting system of equations because, I mean, if we... So let's think about this one for a second. So in this case, I cannot just multiply by a negative number, because if we do that, notice I have x and y. I would have to multiply by x and y at the same time. But in this case, I'm going to propose a totally different solution. I'm going to propose a solution by substitution in this case. So this is what am I going to do. I'm going to grab the second equation. Hold on, I think it's I'm gonna grab the first equation. 2y plus 2 lambda x. And I'm gonna solve for lambda. So 2 lambda x equals to negative 2y, and dividing both sides by 2x, we get lambda equals to negative y over x. And then I'm going to substitute this guy over here where you see the lambda on the second equation, and that's going to eliminate lambda once and for all. So I'm going to have 2x plus 2 times lambda y equals to 0. But what is that lambda? For us is negative y over x. All right, what are we going to obtain here? First of all, let's clean up the parentheses and the negative. So 2x times 2x plus, or rather minus 2y over x equals to 0. Okay, that's going to be squared because y times y is y squared. And now, well, one thing that bothers me here is this x in the denominator, so I'm going to multiply both sides by x to get that solved. So I'm going to have 2x squared minus 2y squared. Notice when I distribute this x over here, so it's 2x times x to x squared, and then this x times this quantity, so x over x cancel out, and on the right hand side 0 times x, which is 0. So I'm going to solve for x here. I'm going to solve for x. So 2x squared equals 2y squared. And then x dividing both sides by 2, we get x squared equals, we get x squared equals to y squared. So for a second, let's leave it. I know what you're thinking. You might want to take the square root on both sides. Yes, we're going to do that in a minute or so. But in the meantime, let me call this equation 4. Okay, let me call this equation 4. So, what are we going to do here? The next step is to combine. Three and 4 to find the critical points. So we're going to find the critical points by combining these two equations. So x squared plus y squared minus 18. Actually, I'm going to go equals 18. Why not? I'm going to write it back again. This one on the other side. Okay, and x squared equals y squared. So in this case, what am I going to do? I'm going to use substitution again. I'm going to replace y squared with x squared, because y squared, which is these two guys, can be replaced with x squared. Okay, so I'm going to get x squared plus x squared equals 18, which is going to be 2x squared equals 18. Divide both sides by 2, we get x squared equals 9. And then take the square root on both sides, plus or minus the square root of 9. And this is going to be x equals plus or minus 3. So our critical points are going to be of the form plus or minus, actually negative 3 comma something, some y, and 3 comma something, some y. How are we going to get the y? So I'm going to go back to this equation right here, equation 4. So I'm going to write it the other way. Y squared equals x squared, and I'm going to take the square root to both sides. So y equals plus or minus the square root of x squared, which cancel out, and that's plus or minus x. So in this case, I'm going to do two calculations. One for x equals negative 3 and another one for x equals to 3. So for x equals to negative 3, I'm going to have y equals plus or minus the quantity negative 3, which is simply plus minus 3. And that plus minus 3, I'm going to put it here. For x equals 3, I'm going to have plus minus the number 3, which is simply plus minus 3. That's all it is. Another plus minus 3. How are we going to interpret this? Well, this one guy right here will be interpreted into two order pairs. Number 1, negative 3 comma negative 3 and negative 3 comma 3. And likewise, 3 comma negative 3 and 3 comma 3. And this is how in this case we get 4 critical numbers. Now, how are we going to find those maximums and minimums? We are going to evaluate these 4 points. Yes, it looks like a lot. However, look at the objective function. It's really tiny, lucky for us. So, I'm going to evaluate f at negative 3, f at negative 3 comma 3, f at 3 comma negative 3, f at 3 comma 3. Okay, so 2 times negative 3 times negative 3, 2 times negative 3 times 3, 2 times 3 comma negative 3, 2 times 3 times negative 3, and 2 times 3 times 3. Let's simplify this. We're going to obtain 3 times 3, which is 9 times 2. That's 18. Negative times a negative is positive. Negative 18, negative 18, positive 18. Now, how are we going to decide which ones are minimums and which ones are maximum? Okay, look at the signs. Largest number, positive 18 is larger than negative 18. Well, by the signs of the numbers, we can call this a real max. Real max. Well, actually, I don't know if we should use the relative max, but anyway, real max. The term real min. Okay, using the signs. So this covers one example of a maximum, one of a minimum, and one in which we look at both max and mins occurring at the same time. So now let's look at applications with word problems. So let's see. So this problem was very classical in Calc 1, but now we're going to solve it in a different way. We're going to solve it using the Lagrange multiplier. So we have a farmer that wants to build a rectangular enclosure along an existing stone wall. The side along the wall needs no fence because the wall already works as a fence. Find the dimensions of the largest enclosure that can be made using only 400 feet of fence. In this case, we are constrained, right? So we cannot just find the max or the min for whatever x, y, like we did in the previous section. So in this case, we have a constraint. Okay. So let's see. So in this case, we want to obtain the maximum area here. So the objective function is a of x, y, which is y times x, so where x times y, that's how we find the area of a rectangle. But what about the constraint? Okay, So in this case, we have 400 feet of fence to enclose some x plus y plus x. In this case, x plus x, that's 2x, plus y equals 400. Now we're going to set up the Lagrangian for this situation. L of x y lambda equals to x y plus lambda times 2x plus y minus 400. Okay, and then over here let's find the partial derivative. So L with respect x, it's going to be the derivative of x. Over here is going to be y plus the derivative of 2x is 2 times lambda, that's 2. Lambda equals the 0. L sub y, it's going to be the derivative with respect to y, which is x, plus the derivative of y, which is 1 times lambda, is simply lambda, set it equal to 0. Let's label equation 1, equation 2, and lambda with respect, the partial derivative of the Lagrangian with respect to lambda will be the constraint. So that is our system of equations. Okay, so what do we do next? All right, combine 1 and 2 to get rid of lambda. So and solve the system of equations. So y plus 2 lambda. Oops, that looks like an x. Let me erase this. Plus 2 lambda equals to 0, and x plus lambda equals to 0. So there's two ways we can go about this problem. Maybe by elimination or by solving for lambda, getting negative x, plug it in here. So there's many ways we can go about this. I'm going to multiply this by negative 2 instead. Okay, I'm going to multiply that by negative 2. But if you decide to solve for lambda and get lambda equals to negative x and multiply this, it's your choice. It's still the same. So this will give us the following system in which the first equation remains the same and the second one becomes negative 2x plus, actually minus 2 lambda equals the 0. Combining the equations together we get y equals to x, y minus 2x, and notice how the lambdas go away, and that equals 0, and y indeed now equals to 2x. Okay, so that's going to be our fourth equation, the equation that later we are going to go back to find the dimension y. So now we combine combine 3 and 4 to find the critical point. Find the critical point. So this is what we do. So 2x plus y, I forgot an equals 0 here, and I'm going to move it at once, 400, and y equals 2x. And here I will easily do substitution. I'm going to plug in this 2xy to get 2x plus y, which is 2x, equals 400, which is 4x equals 400, and dividing both sides by 4, we get x equals 100. In this case, feed, because we have some context going on, which is dimensions of a rectangular area. So we're going to use this equation, the fourth equation, to find y. 2 times 100, which is y equals 200 feet. Now let's go back to our picture to check our job, to check our work rather. So this will be y equals 200, x equals 100, and another 100. 100 plus 200 is 300 plus 100, 400. All right. And those are the dimensions of, in this case, they're only asking us for the dimensions. They're not asking us to find that maximum area. If we wanted to find the maximum area, just multiply 200 times 100, and that's going to give you, give us, I believe, 20,000. Okay, but it's not part of the question. Okay, the following two were problems. I'm just going to help you set them up. So I'm not going to go over the solutions. So in this case, so we're going to have a very similar situation, but in this case, it is to have a division